give you a few bits of introduction to information theory. That's a pun, of course. Information theory quantifies the information in messages. These messages could be man-made, human-made messages, for example, a long string of letters in a radio code, or they can be natural, for example, a long string of amino acids that make up a protein in the human genome. So let's do that second one as an example. Proteins are little three-dimensional machines when they're actually functioning in your body, but they're built out of a set of blueprints, a set of amino acids that are specified just by a one-dimensional sequence of characters representing the amino acids. And it's kind of through the magic of biology that the protein figures out how to fold into its three-dimensional or tertiary conformation. So for example, let's pick a protein that has 261 amino acids in it, and they're each represented by a character in the range of A to Z. Now there are only 20 amino acids that are used by life, so there's a convention for what letters apply to what amino acids, and the convention ends up with A to Z except for these 6 letters that are not used. Anyway, here's a particular protein. The message starts off MAAACR and it ends with RMQP, and if you count these you should find that there are 261 characters. I picked this protein randomly from the human genome, but it's easy given the sequence to search back and find out what it is. It turns out that it's hydroxysteroid 17-beta dehydrogenase, one of many, many dehydrogenase proteins that you have that basically move hydrogen atoms around in chemical reactions. But that's neither here nor there for this lesson. Let's ask a question like this. How many proteins of length 261 are there? Well, there are 20 amino acids that are used in life, and the length is 261, so it seems like the answer should be 20 to the power 261, an astronomically large number, but you're going to see that we're typically working with the logarithms of these numbers, which makes them not nearly so large. Well, in a sense, this is the right answer. But Shannon, about 60 years ago, realized that if the characters in a message occur with unequal probabilities, with some probability distribution p sub I, where I varies over the different, in this case, amino acids, then for long messages there's quite a sharp divide between messages that are rather probable and messages that are extremely improbable. So the information content is in a sense contained almost completely in the rather probable messages. Let's try to estimate how many these are. By the way, the log base 2 of the number of probable messages is the information content measured in bits. Because we're going to end up taking the log 2 to get the content in bits, we might as well start off by defining the number of probable distributions to be 2 to the b. And we can estimate this by the following argument. We know the individual probabilities of the characters, and we know the length of the message, so we know that in this message there are going to be, for character I, about m times pi repetitions of that character. And in fact, as m becomes very large, that estimate is going to become fractionally more and more accurate. Okay, so if that's the number of occurrences of character I, then the total number of messages says take all of those occurrences of all of the characters and figure out the total number of ways those can be rearranged. Well, that's just m factorial from the length of the message being m. And now the number of identical rearrangements that come from just rearranging, or I should say interchanging, all of the same amino acid, even if it's at different positions, that would be this number factorial. And of course, the total number of rearrangements is the product of that number of rearrangements for each separate amino acid. Now to make sense out of this, we're going to use Stirling's approximation, which basically says that n factorial is n over e, that's the base of natural logarithms, to the nth power. This is the dominant term. This going only as square root of n, a very slow variation compared with this n to the n, is the additional prefactor. So back up here, we'll apply Stirling's approximation to the log. So take the log of this side and we get b log 2. Take the log of the numerator, and looking here down at Stirling's approximation, we get m log m over e. Here it is right here. And then we would add the log of this square root of 2 pi n. But that's only the log of n, and that's basically completely lost. Or I should say up here it would be the log of an m. And that's completely lost compared with something that scales linearly as m, so we're going to neglect it. And in the denominator, when we take the log, we get a minus sign, and we get a sum over the logs of these individual terms. And again, applying Stirling's approximation here, the dominant term, the term that scales as m or larger, is this one. Now we can do some simplification on this. The first simplification is to pull the m out of this sum. It's just a constant. And then to expand this log here as a log of m over e, that's the piece that doesn't depend on I, plus a log of pi, that's the piece that does depend on I. So now let's first consider what happens to the mpi times the log of this constant, at least constant in I. Well, the only thing summed over is the sum of the p sub i's, and they're a set of probabilities that are EME, and so they sum to 1. Okay, so this term becomes a minus m log m over e, and look, this whole term cancels this whole term. So all we have left is the thing that we got from the log pi, and it has an m out in front, but it still has a pi here, and so here's the answer. It gives minus m times the sum over I, pi log pi. And that's defined as being the entropy of the message in nats. And the entropy of the message, you see, simply is linear in the length of the message. So over here, we can define this as the length of the message times a property of the distribution only, this sum of p log p. And that's called the entropy of the distribution p. It's useful to think of entropy as measured in units. And because we used a natural log here, we've got out entropy in a funny unit. We've gotten it measured in a unit called nats. If we had used the log base 2 here, which differs just by a constant after all, we would get the entropy in the conventional unit of bits. And in fact, the conversion factor is that 1 nat is equal to 1.4427 bits. This is, of course, 1 over the natural log of 2. So here's our formula again for the entropy of a distribution. Minus the sum over the different characters in the alphabet of the probability of each character times the log of that same probability. Well, evidently, entropy is positive no matter what the values of the p's are, because the pi is positive. The log of a number between 0 and 1 is always negative, but here's the minus sign out front, so that makes it positive. It should be pretty clear that it has a minimum value only in the case when a single p sub I is equal to 1 and all the others are 0. In other words, where there's no uncertainty in the outcome, a particular pi is going to be the outcome. How can we see this? Well, these are all positive. These terms are all either positive or 0, and if you set pi equal to 0, then this is 0. Of course, the log has a singularity at 0, but it's a very weak singularity compared with the limit of pi going to 0 outside the log. So when it's 0, this is 0. But they can't all be 0 because they have to sum to 1. And if one of them is 1, then it's 0 by virtue of the log here. Log of 1 is equal to 0. Okay, so the minimum value is 0. What's the maximum value of the entropy? Well, we can work that out either a long way or a short way. Let's do the long way first because it's not that long. We'll use Lagrange multipliers to simply maximize this quantity, the entropy, subject to the constraint with a Lagrange multiplier lambda that the sum of the pi's equal 1. That is to say, the thing in parentheses here equals 0. So we do this maximization by setting the derivative of the Lagrangian with respect to the pj's to 0. And you can see that for a given pj, we get two terms. We get the derivative of this times this, and that's the minus log pj. And then we get the derivative of the log, that's 1 over pj times pj, so we get a minus 1 here. And then over here, we get a lambda times pj, take the derivative, so we get a lambda. Well, you can rewrite this equation as saying that the log of pj is equal to lambda minus 1. And lambda was the Lagrange multiplier. That's a constant. Therefore, all the p's must be constant, the same constant. And obviously, they all have to be 1 over n, because that's the number of them that there are. Here's the short way of seeing this same thing. The log here that occurs inside is a convex function. This isn't a plot of log, this is just a plot of some generic convex function. But log is convex, and it's of course a property of convex functions that if you average their values between any 2 points, you would get a larger value if you took the value at the average of the points. Okay, well that means that I can keep increasing the entropy by picking any 2 pi's and replacing them by their average. And if I keep doing this, it's obvious that the only endpoint I can end up with is that all of the pi's are equal and are equal to 1 over n. So the maximum value of the entropy is therefore log of n, the number of symbols in the alphabet. In other words, it's minus log of 1 over n, which is the same thing. Let's go back to our example with amino acids. What are the pi's? What is the probability distribution of amino acids in the human genome? So here, shown by letters, are the 20 amino acids. And here is their probability of occurrence. So for example, leucine up here, occurring with a probability of about 1/10, is the most frequently occurring amino acid in the human genome. W, which is this one over here, has the lowest probability of occurrence, slightly more than 100th. You might wonder what this little dot is here in the position that Z is. There, when I was counting amino acids, I also counted stop codons, and that's how often they occur. They're not really amino acids. And of course, these zeros are occurring just because I was too lazy in my plot, and that just means there is no amino acid with that letter abbreviation. So anyway, the probabilities vary over roughly a factor of 10 from 0.01 to 0.1, with most of them clustered somewhere in the middle here. So that's the distribution pi's. It's a little clearer if we give up knowing which is which and just plot those probabilities in descending order. Tryptophan, the least occurring one, is now here at number 20, because there are 20 amino acids. And we can now compute the entropy of this distribution. Here I am in MATLAB, and I'm defining a little anonymous function that is basically the sum of any array of x's of minus x times log of x. Now, I have to teach MATLAB that if x is 0, I want this to come out 0. So an easy way to do that, a little bit of a hack, is add 10 to the minus 99 to the argument of the log, so that that'll still be a fine log, but that it'll be dominated by the x being 0 here. And I want the entropy to come out in bits, not in nats, so I divide by just this constant, the log of 2. So I have this distribution of pi's that add up to 1, and they're in an array called mono. You'll see why in a second. And I'm going to compute the monographic, so-called entropy, by calling this function. Let's also compute what the largest possible entropy would be in an alphabet of 20 characters. As we just saw, that's the log of 20, but again, to get it into bits, I have to divide by the log of 2 here. And the answers are that the largest possible entropy with 20 characters is 4.3219, and the actual entropy of the amino acids in the human genome is 4.1908. So it seems like a small difference. Small differences in bits are measured in centibits. So this is a difference of about 13, it looks like, centibits. But we'll see that that actually can be important. Here's an example. Remember we asked the question, how many likely proteins are there of length 261? Let's now say, how many are there as a fraction of the combinatorially possible number? So the combinatorially possible number is 20 to the 261, whereas the entropically possible number is the entropy that we got down here, 4.19. So the number of states is therefore 2 to the entropy, and then we'll take that to the same power, length of the message, 261. By the way, 20 down here would be 2 to the 4.3219 if you just track it back. Well, this works out to be about 4 times 10 to the minus 11. In other words, only a few parts in 10 to the 11 of the possible space of all possible proteins are actually used by life, because not every random sequence of amino acids can yield a functioning protein. Another way of saying this, if you generated a random sequence of 261 amino acids, it would be very, very easy to tell by looking at its distribution of amino acids that it was not drawn from the human genome. Notice, because we're going to use it a little bit later, that in my MATLAB function for entropy, I took whatever x was. I said it was a one-dimensional array, but it could have been a two-dimensional array of probabilities. We'll see in just a second. And I flattened it into a one-dimensional array by this colon operator before I computed the entropy by summing. And we'll see in just a second that that's the right thing to do. Because the single peptide or monographic entropy is actually only a bound on the true entropy of proteins. And that's because there can be, and there actually is, multiple symbol non-randomness. One way of saying this is, we saw before that only 4 times 10 to the minus 11 of the possible proteins of that particular length, of the combinatorially possible proteins, could actually be reached entropically. The actual number is even smaller than that, because some of those won't have the right two-point statistics, digraphic probabilities. I'll tell you what I mean by that in just a second below. Compression programs try to take advantage not only of monographic entropy, but of any possible redundancy that there is in a file. So a perfect compression program would shorten the length of the file by an amount that's proportional to the entropy. I'll show you what I mean here. Here I took a file of about 9.7 megabytes, which contains the human proteome as a text file of just those amino acid symbols before. And then I compressed it using the zip compression here and the gzip compression here. By the way, these numbers came out so precisely close that my conclusion is that both of these programs are actually using the same algorithm. They're just putting a slightly different header on it. But be that as it may, we can now compute the entropy per bit as follows. The compressed message contains 8 by this length here. I think I chose the gzip one. Okay, number of bits, because this is the number of bytes, of course. Whereas the number of characters in the original proteome was this higher number because they were represented just in ASCII as one character per amino acid. Okay, so the number of bits per character comes out to be 4.556. Well, actually, that's not very good compression. If we used just the monographic statistics of the amino acids, we should have been able to compress to 4.191 bits per character, and zip and gzip didn't even do that well. Of course, they have to be written to compress very general files, not just files of amino acids. So let's look at digraph entropy, and now I'll tell you what I really mean by that. Here I'm displaying graphically a table of 400 numbers, that is to say 20 amino acids by 20 amino acids. And as a heat map, it shows probabilities that should all add up to 1. And it's the probability of a digraph, that is, a certain amino acid, one of these symbols up here, followed by, immediately, a second amino acid, which is one of these symbols down here. So you can see from the heat map that the most common digraph is L, our friend leucine, followed by L. But another common one would be L up here, followed by S, serine, down here. Whereas C, for example, is pretty uncommon itself, so that C followed by almost anything has a small probability, as you can see from the dark colors of the heat map here. This is just a way of displaying the 400 numbers. Now, what's the digraph entropy? Well, that's our same entropy function can be used because, as I commented, it'll just take these 400 pi's adding up to 1, flatten them, and compute the sum of p log p on them. And that turns out to give 8.3542. But that's the number of bits that it takes to encode 2 characters, the whole digraph. So to see what's the equivalent monographic entropy, we would divide that by 2 and get 4.177. Indeed, that's lower than our calculation previously, 4.191 up here, and it shows that there is some additional information in the second order statistics, in the digraph statistics of the amino acids. Well, we can go on the same way, and we could look, I'm not going to plot it for you, at all 8,000 trigraphs and how often they occur. That's in a three-dimensional array here called tri. I run it through the same entropy function. I get that it's 12.5 something bits, but that's now encoding 3 characters. So I'm spending 4.168 bits per character. And indeed, there's a little bit, just about 1 centibit of information gained in looking at the trigraphs instead of the digraphs. We'll see later that it's a mathematical theorem that these numbers have to decrease. But as you see, they don't have to decrease by much. In general, as you go to higher n graphs, the gain in entropy is going to get smaller and smaller. And the true entropy, the actual information content of the message, would in some sense be the limit as n becomes large of the n-graph entropies. So entropy, sum of p log p, has various uses, or as it says here, interpretations. The one we've been seeing up to now is that it's the binary message length of the maximally compressed message. That is to say, if a message contains only 2 bits per character, then it can actually be compressed down to 2 bits, 2 ones or zeros per character. And the way you can see that at a high conceptual level is that entropy divides the probable messages from the highly improbable messages, you could just send the binary serial number of your particular message among all probable messages. And then what if you ever got an improbable one? Well, you'd have to do something else, but that something else would occur exponentially rarely and not add anything to the mean length. Something else would be like an escape code signaling what I'm about to send you is not a serial number. But here's a second interpretation. Suppose we have an experiment. I'm going to stop and check the volume here. Here's a second completely different interpretation of entropy. Suppose that you have a large number of hypotheses about something, and you can measure a feature of those hypotheses, and some of the hypotheses will come out with feature value 1, some with feature value 2, and so on up to n. So that if you measure that feature, you'll be able to eliminate all the hypotheses except the ones that have the measured answer. Okay? Now, on average, by what fraction, or we might say how much in the log of the number of hypotheses, are you going to be able to reduce if you examine this feature? Well, the answer is that each feature occurs with probability pi, but if that feature in fact is the one you measure, you'll be able to decrease the log of your number of hypotheses by log pi. Let's see how that works. Suppose that you come out and you measure a feature that only occurs 10% of the time. Well, then 9/10 of the hypotheses will disappear, or another way of saying that is you'll be able to have reduced the log of the number of hypotheses by the log of 10. Okay? So what's the ideal distribution of outcomes for the best possible experiment? If you think about it, you'll see it's the expectation value of the log of the pi, and that's just pi times log pi, which, except for a minus sign, is just the entropy. So the entropy is a figure of merit for which features you should try to measure. You should try to measure the feature whose outcomes are most uniformly distributed, because the uniform distribution of outcomes has the maximum entropy. Well, here's a third application where entropy comes in. I need to introduce you to the idea of a fair game. We're going to make bets on something, and then we're going to get a return if our bet comes out to be true. So here, the PIs might be the probabilities of different horses winning in a horse race. Now, if our horse comes in, which happens with probability pi, we expect to get back a return on our bet, and that will be the payoff labeled OI. And what would be a fair game? A fair game would be one in which if we bet $1, on the average we make $1. So the average of our payoffs should be the expectation value of OI, but we're betting just on outcome I, so basically our payoff is only that payoff with probability pi, and we want that to be 1. Okay, this is just a long way around of saying that in a fair game, your payoff should be the reciprocal of your probability of winning. Now, what does this have to do with entropy? Well, I want you to take you to the fanciful world in which you have complete predictive information on the outcome of every horse race. You simply know at the beginning of the race which horse is going to win, and you bet on that horse. Well, can you make an infinite amount of money? No, because you start with $1, and in each horse race you only can win a finite amount. Even though you're betting on the winning horse, that winning horse will pay off only with odds of 1 over its probability. You don't get to control which horse wins, you only get to know which horse wins. Well, if you think about it, the log of your capital growing from $1 to $2 to $3.72 or whatever to $8 and so on, the log of your capital will increase with each race by the entropy, because it's essentially the same calculation as up here. You get a payoff each time of, in the log of the pi, or rather minus that because it's log of OI, but that occurs only in each race with probability pi, because you don't get to control which horse wins, you only get to know which horse wins. So a way of saying that is the entropy is the e-folding, that's if it's in nats, or doubling if it's in bits, rate of capital for a fair game in which you have perfect predictive information. This seems fanciful, but we'll come back to it in the next segment and you'll see that it's really kind of interesting.